This is seminar number 3, or seminar lab session 3. And in the first part of this seminar, we considered the VO2 equation, so the equation for calculating oxygen consumption, so VO2. So I'm going to take you through this, and then there'll be some other bits and pieces that we also did in the lab that are going to be on subsequent videos. So this VO2 equation, the idea of this session is, or the whole seminar I should say, was to link up what you already knew from first year with regards to oxygen consumption, and then where we were going to take it for, or where we are going to take it in second year. Now in first year you have calculated and measured oxygen consumption, so VO2, many times before, so several times, and you did it using a Douglas bag technique. So this is a technique where you fill up a Douglas bag, and then you kind of after you've taken a sort of minute sample to get expired air, then take it to some machines that give you these values. You take the values, you put it into some equations, and then you use that to calculate your oxygen consumption. And then this year, the way we're going to move this forward is we're going to be using a completely different technology, so a breath-by-breath gas analyzer, which sort of does a lot of this work for you. And so one of the primary the primary reasons for doing this session is to highlight, to contrast these two different ways of coming to the sort of same answer, to the same conclusion of calculating this oxygen consumption. So the first off, what we're going to do is we're going to go through the oxygen uptake equation. Now this is because this is really the fundamentals of oxygen uptake. If you understand the equation, which is really simple, or this simplified version, you can understand how that fits in with what you've done with regards to using Douglas bags, and you'll also have a sense for how the new breath-by-breath gas analyzers work in order to get you back to these same values. So we're going to go through this equation bit by bit, and don't turn off because it's an equation, because it's really, really simple, and my job now is to kind of show you how simple it actually is. So we've got VO2. So V stands for volume. So the volume of O2, which hopefully you realise is oxygen. So O2, diatomic particle oxygen, so it's O2. And then we have this thing above the V, which is this dot. Now during questioning in the actual seminar sessions, people were able to identify all the different elements of this equation. Maybe not a single individual was able to identify all, but as a group we got the whole thing. So what's the importance of this? So firstly, I highlight the fact that the most common mistake that people make when they're writing is to, rather than write VO2, so the volume of oxygen, they write V02. So this is where I've highlighted it here. So it's VO2 with this little dot, not V02. So VO2 means volume of oxygen. V02 means absolutely nothing. That's the volume of nothing. And it's also not the volume of oxygen squared, because that means nothing either. So you have to get this right when you're writing a report, because this is our primary outcome variable. And by getting this incorrect, which around 15 to 20% of people do when they submit, it infuriates me, because it tells me that you have not been paying attention to the whole year's worth of lectures and seminars, because we talk about this almost every single week. So make sure you get this right, and we'll do another session on it a bit later on in the year. So it's V, volume, O, oxygen, 2, because it's a diatomic particle, and then there's this dot. And people correctly identify that this dot is to signify something as a rate, so it's per unit of time. And this is important because if you think about it, without this dot, if we say the volume of oxygen, so let's say you breathe out into a Douglas bag and you breathe out for 2 minutes, and you breathe out maybe, let's say your volume is 10 litres in 2 minutes. Well, if you breathe out for 4 minutes, your volume would be 20 litres. So knowing the volume of oxygen doesn't really mean very much, because it's going to be dependent on how long you're breathing out for. So what we do is we kind of almost standardize that slightly by putting it over a unit of time, because what we're interested in is the volume of oxygen you breathe out per minute, because that way we can compare and contrast different people and also at different time points. So if you've got a volume of oxygen per minute of say 1 litre at rest, and then it goes up to say 4 litres during exercise, we kind of know that actually means something. It doesn't just mean that we've collected a sample for a longer period of time. So it's volume of oxygen per unit of time. So our oxygen consumption equals, so this part of the equation sort of comes under the sort of inspired side. So the volume of oxygen equals the volume of inspired air. So V volume, I inspired. We're talking about air here, per minute, the dot, times the fraction of inspired oxygen. So go through that again. The volume of inspired air per minute times the fraction of inspired oxygen in that air. So one of the things that often confuses people here, they're usually happy with the volume, they're happy with it's inspired, like how much air you're breathing in, and now they're usually happy with that we're considering it over a unit of time. So the only thing really that can confuse people is this F, the fraction. So if that does confuse you, if that's not very intuitive for you, one of the things that you can do is to just, rather than think about it as a fraction, which it needs to be for the equation, but rather than thinking of it like that, think of it as a percentage. Because really what this is the same sort of thing as it's saying, what percentage of oxygen is making up the inspired air that you breathe. And so just to sort of think about the relationship between fractions and percentages, it's a really simple one. So a percentage is 100 times higher than a fraction. So if you look at this chart at the bottom here, if we've got 100%, the fraction is 1, 0%, the fraction is 0. And then if we look at some of the numbers that are going to be close to what we're going to measure, so 20%, so let's say the fraction of our inspired oxygen was around 20%, then that would account for a fraction, the percentage of our inspired oxygen is 20%, that would be correlate to a fraction of 0.2. So if you're struggling with fraction, if it doesn't make sense, it has to be a fraction for the calculation to work, but to think about it, you can consider it to be a percentage divided by 100. Right, so that's the inspired side. Now, the next bit is a minus, and then we'll go to the expired side. So hopefully you're going to be able to make sense of some of these letters here. So we've got V again. So minus the volume of expired air per minute times the fraction of expired oxygen in that sample of air. So that should all be fairly okay now. So what does this actually mean? So what it's saying is the volume of oxygen consumed is equal to the volume of oxygen inspired minus the volume of oxygen expired. So just think about this, because it's fairly simple. If we breathe in a certain amount of oxygen and then we breathe out less, then something has to have happened to that oxygen. It has to have gone somewhere. And so what happens to it is it has been consumed by the body. Oxygen consumption, or it's been utilized, oxygen utilization. So let's say we breathe in a certain amount, we breathe out less, so some's gone missing. Where has it gone? We've used it. We've used it to resynthesize that ATP, and we've turned it into CO2. So that's the basis of the equation. VO2 in litres per minute equals volume of air times the fraction of inspired oxygen in that air minus the volume of expired air times the fraction of expired oxygen in that expired air sample. Right, so the next question is, well, where does this information actually come from, and how does this relate to the labs that you've done in the past? Because what I want to show you is that actually in the past you've been measuring these things, you just probably haven't really been thinking about it in this way. So what we're going to do is go through the equation and then consider where this information actually comes from with regards to what you're doing when you're doing a Douglas bag lab, which you've done last year and you've also done this year. So again, VO2 equals, so we're going to go straight to this side of the equation, so the expired side, because this is an inspired side here, because this is all related to the air that you inspire. This side here is all related to the air that you expire. So How does it relate to what you do in a lab? So first off, when you're breathing out into a Douglas bag and you're collecting that sample, so this is your Douglas bag here, that takes care of the expired part of it. So if you're expiring into the bag and collecting an expired air sample, that means that everything that we measure that's in that bag is going to relate to this expired side of the equation. So the E part, if you like, takes care of the expired. And what's important to note is that if you want to calculate VO2, you have to know each part of this equation. So there are 4 elements and you have to know each one. If you don't know one of the elements, you can't work out oxygen consumption. So the expired side of both of these 2 parts of the equation are taken care of because we take an expired air sample. Now, the next part is, well, where does the volume come into it? So the V. Well, the V comes into it because once we breathe out into this bag over a certain period of time, we collect this expired air sample. Well, actually, let's do the fraction first. Let's change tact. So where does the fraction come from? So we breathe out into this bag, which collects our expired air. And then the next thing that we do is we put it through this thing called a Servomex. And all a Servomex does is it measures the percentage or fraction, because it's the same thing, of oxygen and CO2 whatever it's being put through it. So when you leave it alone and you don't attach it to anything, it tells you what the fractions of gases are in the atmospheric air. When we attach it to this expired air sample, it tells you a fraction of expired oxygen. Well, actually what it tells you is the percentage of expired oxygen, and then we divide it by 100 to get a fraction. But that's what it's doing. It's telling you this number here. So when you're doing your labs and you're measuring your oxygen percentage on the Servomex, you're doing it to take care of this part of the equation. So you're working out your fraction of expired oxygen. So the next part is, well, where do you get your volume from? So once you've got your fractions of gases, the next thing that you do is you use this vacuum type of machine, or it's attached to a vacuum, I should say. This is a dry gas meter. So you'll remember that what you do is you attach your expired air sample, the E, to this dry gas meter. Then you turn on a vacuum which sucks the air through the dry gas meter, which counts the volume of air in that sample. So it counts how many litres of air are contained within your expired air sample. So we've got the expired part again, because it's expired air sample. The dry gas meter counts up to tell you the volume in that sample. So the only thing we're missing then is the rate. And the rate relates to, well, how long did you collect that sample for? Because if it's a 1 minute sample, this is going to be the volume of expired air per minute, which is the units that we want it. If it's over 2 or 3 minutes, then you'd have to divide it by the number of minutes to turn it into sort of litres per minute. So if you think about this, when you're in a lab, all the things that you've been doing all relate to the expired part of this equation. And that's why it's called an expired air lab, or why you're looking at measuring expired air sample. That's why we always talk about that, because it's all on the expired side. So just to reiterate, you collect an expired air sample, you run it through the Servomex, which tells you the fraction of expired oxygen. You then evacuate the sample through the dry gas meter that counts up how many litres were in that sample, so that you get the volume of expired air per minute. So you've taken care of these 2 elements of the equation. So the next question is, well, what about the other side? So what about the inspired side? Now, importantly, and it's worthwhile bearing this in mind, that we never measure anything on the inspired side. So we don't measure the volume that you inspire, obviously, because we're collecting expired air samples. So we're never measuring how much goes into the body, we're just measuring how much comes out. And we don't measure the fraction of inspired oxygen either. So the question is, where do we get these values from? Because if we don't know either of these, we can't work out VO2. So measured, don't know. So what do we do about this? Well, the next part we're going to work out, think about, is this fraction of inspired oxygen. So when I ask this in the class and say, well, what is this fraction of inspired oxygen? There's usually only 1 or 2 people who are able to come up with the right answer. And it's a fairly simple one, and that is that this is a fixed fraction. So it's a constant, and it's a constant because if you think about it, we're always breathing in from the atmospheric air. So our fraction of inspired oxygen is always 0.21 or 21%. So the amount of oxygen in the atmospheric air is 20.93 or about 21%. So that means that our fraction of inspired oxygen is always 0.21. So this part of the equation never changes. It's a constant. Doesn't matter where you are in the world, doesn't matter who you're testing. The fraction of their inspired oxygen is always going to be 0.21. So we know this is a constant, so we can tick it. So then the final part of the equation, it also happens to be the most difficult to kind of work out, is the volume that we inspire. So we don't measure the volume that we inspire. What we do is we estimate the volume that we inspire based on the volume that we expire plus a few corrections. So what we did in the lab, to just sort of illustrate the simplicity and so people kind of work out their results based on what they found from their sample straight away, is we said that actually for our purposes, the volume expired is going to equal the volume inspired. So we're just going to substitute this value here for this value, just to get the idea. And you can imagine that this actually is, approximately correct. Because if you're breathing out at 10 litres per minute, there's a likelihood that you're going to be breathing in, say, 9 to 11 litres per minute. It's unlikely that you're breathing in 50 litres per minute and only breathing back out 10. So there is a strong correlation between these two values. They're not exactly the same, and that is why when we're actually doing the calculations properly, we take that into account. So we do a thing called the Haldane transformation, which is where you take into account the VE and then the respiratory exchange ratio, which allows you to get a better estimate of the VI. But considering VI to equal VE gets you about 90-95% the right answer. So they're really close. It's a subtle differences that you make by doing the Haldane transformation. But for us, because we want to keep it simple and I want you to be able to relate what you're doing in the lab back to this equation, we just considered it to be exactly the same. So if we go back to the equation at the bottom, just to kind of go back over that one more time so we can think of it like this. So we're looking to measure VO2, and you've been doing these labs for over a year now. And I want you to be able to now go, actually, I understand why I was doing what I did in the lab and what I'm going to do sort of in the subsequent labs. So that is our volume of oxygen consumed, used per minute, is equal to our VI, so the volume inspired, which we're going to estimate from expired volume, times the fraction of inspired oxygen, which is always 0.21%, or a little bit, 0.21%, sorry, 0.21 or 21%, minus the volume of expired air per minute, which we measure using our expired air sample in a Douglas bag, running it through the dry gas meter, and the fraction of expired oxygen in that air, which we calculate or we measure using the Servomex. So we measure this, we measure that, that's a constant, and then we estimate that from VE. So one final kind of attempt to sort of illustrate this, and so you get the kind of point of what's actually happening when you're measuring this expired air. So think of it like this. So on this side of the equation, so we've got VO2 equals all of this to do with inspired. So what this is saying is, like, what is the volume of air you're inspiring? So let's say our volume is represented by this circle. Now the volume of air is made up from CO2, O2, nitrogen, and some other molecules as well in small amounts, but mainly it's nitrogen and oxygen. So this whole volume is largely made up by nitrogen and oxygen. And let's say in our particular example here, 25% of the molecules that make up this volume of inspired air is made up of oxygen. So 25%, a quarter. So now let's say that's our expired air sample has the same volume. So VE equals VI. So the volume is the same, but now we're breathing out less oxygen than we consumed, which should hopefully make sense because we have a sense that we're using oxygen. So In this case, V is the same, so the size of this circle is the same size as this circle. So the volumes are the same, but in our expired air sample, there is now the fraction of expired oxygen is less. So now this sample is made up of other gases. So nitrogen and largely some more CO2, which is going to make up the difference. So now, if we go to this formula, put some numbers to this. So let's say our inspired air, so our VI is 20 litres. So if we take 20 litres and times it by a quarter, so this is a quarter of a circle here, because that's the amount of that inspired air that's made up of oxygen. That gives us an inspired oxygen volume of 5 litres. So 20 litres, divided by a quarter or times 0.25 gives you 5 litres. And then we take away, again, 20 litres for the volume of expired air. This time times 0.2, because it's now a fifth, so a lower fraction, now gives us 4 litres. So there are 5 litres of oxygen in our inspired air. There are now only 4 litres of oxygen in our expired air. So our VO2 is then going to be 5 litres here minus 4 litres there, which would give us a VO2 of 1 litre per minute. And that is fundamentally what you're trying to do. So we're measuring our VE, the circle, through our dry gas meter. We're measuring the fraction of expired oxygen through our servomex, which is this bit here, how much of this whole sample is actually made up of oxygen. And we're timing them together to work out this. We know that our fraction of inspired oxygen is 21%. So slightly different than the example, but the numbers are easier. And then we're going to times that by our volume of inspired air as well. We measure the difference between the two. Well, where has that oxygen gone? That oxygen has been utilised by our body to resynthesize that ATP for energy production in order to, say, run or cycle or whatever else we're doing. So that's the end of this sort of section. The idea of it is that this is the only time that we're going to do Douglas bags this year within this module. But before you can really understand what's happening with a breath-by-breath gas analyzer, you really have to understand this, because what the breath-by-breath gas analyzer does is it does all of these equations for you and then kind of pumps the number out at the end. And so unless you have an understanding of what's actually going on, it can kind of become quite confusing. So what we're going to do in some of the subsequent mini videos is I'll give you a demonstration of how a breath-by-breath gas analyzer works, how the sort of software, how to navigate through the software, and then we'll start to sort of see some exercise tests using this software, and you can kind of compare to what would be how long it would take you to do a Douglas bag sample. So one of the major take homes from this that I was trying to get across in the seminar or the lab was that I then got the students to do a Douglas bag sample collection from start to finish. So putting the mask on, collecting an expired air sample, analysing the samples using a servomex and a dry gas meter, then taking the values that they've got, inputting them into the equation to then get a VO2 measurement. And it was taking groups anywhere between about 20 and 30 minutes to do that. And then I was showing them how much easier it was to do this using a breath-by-breath gas analyzer. So that's the sort of first section of the lab. Hopefully now you'll be able to link in what you've done in the lab for your Douglas bag sessions and your expired air sessions, how it works this equation, and then you'll have a great consideration to how that relates to what we're doing with our breath-by-breath gas analyzers.